So thank you. It's a great pleasure to join you at this gathering. And I'm going to focus my attention on an area of physics that I think fits in well with the themes that you have been hearing about in other arenas, other areas, because I'm going to be talking about the science of black holes. And this is a particular area that demonstrates how those ideas that may seem ridiculous or crazy to one age can ultimately not only be experimentally and observationally supported, but in a next age can migrate to canonical form, to everything that everybody always thought was true, everything everybody thought was right. So in a way, if I was going to give one takeaway message, if I can use that unfortunate language for what I'll be talking about here today, it's that skepticism is an art, not an algorithm. And that's absolutely vital. Because when you approach certain ideas as if there is a fixed set of criteria by which you're going to judge the things that you consider to be true and the things that you do not consider to be true, you can inadvertently cut out a whole collection of ideas that you simply at that moment in time don't have the intellectual architecture to judge. And that certainly is the case with the science of black holes. Now, I recognize that people come to this gathering with a whole variety of different backgrounds. There are some of you who no doubt could stand up here and give the talk I'm going to give. There's some of you for whom these ideas may be familiar from popular culture, but you've never really dove in and grappled with them fully. So in order to give everybody a little bit of something, I'm going to start fairly basic, and then as I get toward the end of the talk, I will be taking on things that are right now at the cutting edge. And as Barry just mentioned to me, since this is the last talk, there's no place that anybody has to get to. So I think probably sometime within 4 or 5 hours, we should cover everything that I'd like to cover. No, so toward the end, as I migrate into more of the cutting edge thinking about things, I will try to draw a fairly sharp line between those things that we now have great confidence in because of observation and experiment, and those things which are still in that fuzzy but fertile place where people are developing the ideas and we don't yet know if they are right or wrong. All right, so to get into the subject, black holes, it's an area of investigation that relies upon our understanding of the force of gravity. So to get us all on the same page, of course, the first person to really think deeply in a quantitative way about the force of gravity is Isaac Newton. And if you cast your minds way back to the late 1600s, again, a very different era than the one that we experience, a time, in fact, when the Black Death was waging a winning war against humanity. And to escape the scourge, Newton retreats to his family's home in the countryside of England. And there, in pretty much isolation, but using the power of thought, the power of calculation, the power of curiosity, the power of wonder, the power of observation, Newton won a very different kind of battle for all of us. Because by the time it was safe for him to go back to the University of Cambridge, he would throw into dazzling relief a fundamental fact, a fundamental law about how the universe works. And that, of course, is the law of gravity, the universal law of gravity. It's a law that we still teach to kids around the world. You all know it. F equals G, M1, M2 over R squared. That wasn't meant to be funny, but I'm glad someone thought it was humorous. There it is, the law of gravity on a T-shirt. Now, if you're not into equations, the way of thinking about it in pictorial form is this. You've got say, a star, think of it like the sun, a planet like the Earth, and using that little bit of mathematics, we can make predictions for where the planet should be at any given moment. And the wonderful thing is you look up into the night sky, and the planets are just where the mathematics says that they should be. So this was one of those astonishing moments in the history of intellectual thought, where a whole collection of phenomena taking place out there in the heavens and, in fact, down here on Earth was encapsulated in a little piece of mathematics articulated by a handful of symbols that, indeed, as we saw, can fit on a T-shirt. Now, when something like that happens, it captures people's attention, right? That's not the end of a story, right? That's the beginning of a story, because now you can take an idea which was previously only understood in a qualitative sense, and now you can put quantitative power, mathematical rigor behind those phenomenon, and in that way try to go further. And that's what a number of people did after Newton gave the world his universal law of gravity. And in particular, some began to think about a very simple pedestrian concept, which is the concept of escape velocity. So once you understand gravity, you can ask yourself the question, if you say have a planet, let's focus on planet Earth, and you have a cannon, you can ask yourself what happens if you fire the cannon, say, in a vertical direction. Now, of course, if you just give the cannonball a little bit of a kick, we all know what happens. Goes up, comes down. In fact, using Newton's laws, you can predict exactly how high it will go. It's a simple and traditional high school problem to do so. Now, if you give that cannonball a little bit of a stronger kick, it goes up higher, still, of course, comes back down. But according to Newton's law of gravity, you give that ball enough of a kick, and it won't come down. It will escape the gravitational pull of the Earth. And in fact, using that equation on the T-shirt, you can calculate the speed that you need to give the cannonball in order that it will not come down. And the answer is? That's right, the answer is? Escape velocity. Escape velocity, what's the number? Yeah, I don't know, Miles, but I should know it, but that sounds right. It's about 11 kilometers per second, so whoever said 7, was that you? Very good. I think, applause for the gentleman in the second row there. Good. All right, so that's absolutely true. But now an interesting theoretical question comes to mind, which is this. That number depends upon the size of the Earth. So the question people asked was, well, like, what if you make the Earth bigger, right? A bigger planet, and you want, again, to cause a cannonball to escape? Well, you need a more powerful cannon if the planet is larger. And again, using Newton's laws, you can calculate, kick it with a sufficient speed, and it will escape the pull of that planet. But then an interesting question comes to mind from that, which is, what if you're firing not metallic spheres? What if you're firing balls of light, photons? Well, photons, they have a speed, right? They have an intrinsic speed, right? I can poll the audience again, but it will depend upon the units that you like to use. Some wise person will say, well, it's 1 in the appropriate units. But, which is true. 186,000 miles per second, 671 million miles per hour, 300 million meters per hour, whatever unit you like, there is a speed of light, right? And that is a number. And you can ask yourself, well, since that's such a large number in a situation like this, you anticipate that it won't be too hard to cause that light to escape. But this fellow right here, a clergyman named John Mitchell, he wondered way back when what would happen if you had, say, a star, which, if you think about it, a star is nothing but a sequence of light cannons all around the surface of the body that are firing balls of light outward. And the question is, if you have a star and you imagine it getting ever more massive, then the escape velocity will go up, and at some point you can imagine making the star so big that the escape velocity is bigger than the speed of light. What then would happen? Well, the light would go up, come down, it would not be able to escape. So this is the earliest incarnation of an idea of a black hole. It wasn't called a black hole back then, but it's the same basic idea. A body whose gravitational pull is so powerful that light cannot escape. Now here's the thing. This analysis that was done by Mitchell way back 1700s using Newton's laws of gravity, but Newton himself knew that his understanding of gravity was incomplete. However powerful it was, he recognized indeed that there was a missing piece, and he wasn't happy about this. In fact, he was kind of embarrassed by this recognition, because although he had written down a formula that gives you the strength of the gravitational pull of a massive body, he was unable to answer the question of how gravity actually exerts its influence, right? I mean, if you have the sun here and you have the earth here, you've basically got empty space between them. And Newton wondered, and he pondered, and he couldn't figure out how it could be that one body over here could affect another body over here without any mutual contact, right? That's the kind of idea you look at it, and it is crazy. How could a body exert influence across the vacuum of empty space? This is the question that Newton asked himself, and indeed, in his Principia, he writes that the answer to that important question, how gravity exerts its influence, he said, I leave that to the consideration of the reader. All right? He knew it was an open problem. He couldn't figure it out and said, you figure it out, right? And nobody could figure it out, right? Most people didn't even think about it until one particular unusual thinker who could look at things in a different way came along. And Albert Einstein had that uncanny ability to look at the most basic of questions and just see them differently. So starting in about 1907, Einstein focuses his attention on trying to figure out how the force of gravity works. And others at the time, some of the most respected, insightful physicists in the world said to Einstein, do not work on gravity. It's too hard of a problem. Even if you make headway, no one's going to believe you. You're going to ruin your career if you focus on a problem of that nature. And these were the kinds of people whose advice you should trust, right? These were the individuals that had transformed our understanding of the world in an earlier era, an earlier generation. And yet the whole power of science is that you can have new thinkers come along and basically say to everything that happened before, okay, got it, but I'm going to go in my own direction. And that is the kind of thinker that Albert Einstein was. So he stays with this problem, goes against the advice, and by 1915, about 10 years later, he comes up with what he believes to be the answer for how gravity works. I think many of you are familiar with the idea. For those that aren't, let me just say it in metaphor first, and I'll show you a little visual on it. Einstein basically says, look, if the puzzle is, you got the sun here, you got the earth here, and there's only empty space between them, right? So how could they be influencing each other? He says the only way they can influence each other must be to make use of empty space itself. Empty space itself must be able to do something. It must not simply be an inert backdrop, right? It must actually be part of the dynamical unfolding. And that's a startling idea. And yet it's the one that he pursues and ultimately turns it into a rigorous mathematical formulation. So the metaphorical version goes like this. Forget about gravity in the universe for a moment, a little complicated. Instead, think about a rubber sheet that's stretched nice and taut between us right here. Imagine I take a marble and I set it rolling on the surface. In your mind's eye, you can picture exactly what will happen. The marble goes in a nice straight line trajectory. Nothing complicated. If I now change the situation a little bit, I take a bowling ball, put it right in the middle of the rubber sheet. Now the sheet's curved, it's warped. In your mind's eye, take that marble again, set it rolling, and you can picture it doesn't go in the same straight line trajectory any longer. Now, instead, the marble goes in a curved trajectory because it's rolling on the curved surface of the rubber sheet. That's the basic idea, but now we take it over to the universe. Instead of a rubber sheet, space. Instead of a bowling ball, think of any astronomical object, and the idea is merely by virtue of that object's presence within space, it curves, it warps the environment around it, and that curvature affects the motion of other bodies that are moving through that realm. So, in visual form, it looks like this. So, this is 3D space, a little hard to picture and work with, so I'd like to go to a two-dimensional version that will capture all the ideas. So, as you see, space is flat when there's nothing there, but if we bring in a massive body like the sun, the fabric curves. And the Earth, too, it also curves the environment around it. And now focus your attention on the moon, because this is the point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. This, according to Einstein, is how gravity works. And if you pull back, you see that the Earth is kept in orbit for exactly the same reason, rolling along a valley in the curved environment that the sun creates. That's the beautiful picture that Einstein comes up with. And again, it's not just pictures, animation, there's mathematics behind this, right? Slightly more complicated mathematics than Newton's formula that we teach to high school kids, but there you see it again, fits nicely with the right font size on a t-shirt. And that mathematics allows you to make predictions. So Einstein does make a prediction, and the prediction has to do with the motion of distant starlight as it travels across space to the Earth in two circumstances. The first one here, when the Earth is on that side of the sun, compared to 6 months later, when the Earth is on the other side of the sun, and that light has to go through the curved region near the sun. And his mathematics predicts the angle between the straight trajectory 6 months earlier and the curved trajectory 6 months later. And that prediction is ultimately borne out through observations that took place on May 29, 1919, so just over 100 years ago. And indeed, his prediction is confirmed. As you see, men of science, more or less agog over results of the eclipse observations. Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry. On September 22nd, 1919, Einstein gets a telegram alerting him to the success of the observations. He's with a student at the time, Elise Schneider, and she says to him, "Professor Einstein, what would you have said had the observations not confirmed your prediction?" And Einstein famously said, "I would be sorry for the dear Lord, for the theory is correct." So with that great success, again, people notice, people pay attention. And one particular mathematician, scientist named Karl Schwarzschild, who at the time was actually stationed at the Russian front during World War I, he starts to think about Einstein's ideas and comes to sort of an amazing conclusion. So there he is. You know, he's supposed to be calculating artillery trajectories, but he finds that kind of boring. So, you know, he's just sitting there in the trench doing other calculations, and sort of amazingly, luckily for him, fortuitously for us, Einstein's manuscript just happens to float out of space, drops into his hand. A hand, I should say, for you skeptics, that looks just like my hand for whatever reason, but he starts to calculate with Einstein's manuscript, and he realizes that if you have a spherical body and you crush it down to a sufficiently small size, the warp in the fabric of space will be so severe that nothing that gets too close will be able to escape, and that nothing even includes light itself. So here we have another version of John Mitchell's idea that he derived using Newton's view of gravity. We see it reappearing in Schwarzschild's analysis using Einstein's more refined version of gravity. So once again, we have the possibility here of an object that will not allow light to escape and therefore is black, a black hole. So in the Einsteinian description, it'd be something like this. The warp in space is so deep that if you turned a flashlight on in the vicinity of this curvature, instead of the light going out into space, where you say could see it if you're far away, the light gets pulled into the gravity well, and therefore that region looks dark. Now this, of course, is an animation of the mathematical description. What would an object like this actually look like out there in space? Well, since it's black, it would be hard to see, but objects are always in an environment, and that environment often has gas and dust particles. So this is what it would look like, something like this. You have dust and gas swirling around this region, which itself is dark. We can see the light from outside the region, and that's what allows us, in principle, to recognize that one of these objects is there. Now, when Einstein learned about these black hole solutions to his equations, to his theory of gravity, he actually did not believe it. And it took me a while to find what I considered to be, a nice skeptical expression, if you will, on Einstein's face, right? And it's not hard to understand why Einstein was indeed skeptical that these black holes would actually be real. There are a number of reasons. Some are technical, but others are fairly straightforward to grasp. When you put numbers in to figure out the amount of crushing that you need to exert on a spherical body to create a black hole, the numbers seem absurd, right? So to turn the sun into a black hole, you'd have to squeeze the entire sun to a couple kilometers across. To turn the Earth into a black hole, you need to crush it down to about half an inch across. And I didn't actually come here with, say, a model of the Earth as a black hole, but as I was contemplating my remarks just 15 minutes ago, Ray, is that correct? Yes, in the front row here, completely independently showed up with an engineered sphere whose size is exactly what it would need to be to turn the Earth into a black hole. Not quite as heavy, but nevertheless it gets the size right. So thank you for the prop. But as you can imagine, if you talk about crushing the Earth into this, that seems ludicrous, right? That seems absurd. And that's why Einstein did not warm to this idea. But thankfully, when Einstein frowned on this idea, people didn't give up, right? It's not as though you look at the master of an earlier age who had seen much further than anybody else and somehow you accord them some kind of extra right to truth, right? That's, at that stage, an informed opinion, but it is not truth. So others stayed at it, and indeed they came up with a mechanism, a physical mechanism that might actually crush an object like a star or a planet to a fantastically small size. And that mechanism goes like this. So imagine you have a large star, say a red giant. This star supports its own enormous weight by nuclear processes that happen deep in the core that generate an outward pressure. Now, sooner or later, every star will use up its nuclear fuel. And when that happens, you don't have an outward push any longer, so the star begins to implode in on itself just by its own weight, the force of gravity, that makes the center hotter, denser. Ultimately, it explodes, setting off a shock wave that ripples through the various layers of the star, and when it gets to the star's surface, it blows off the surface in, of course, what we call a supernova explosion, and what remains can no longer support its weight at all, and therefore just collapses right down to an arbitrarily small size, collapses into at least what the mathematics says would be a black hole. So now, not only do you have the mathematical possibility that black holes will be out there, you now have a mechanism by which you can imagine them actually forming. That's good, but it's still not actual observational evidence. And the first evidence came from studying our own Milky Way galaxy. In the center of our Milky Way galaxy, we believe there is a black hole, and you can begin to see why as you look at the trajectories of stars that get whipped around the center of our galaxy. This is based on real data, and you can see that stars are being whipped around at speeds of upwards of 10 million miles an hour. And when you look at what object in the small region at the center could exert the gravitational pull to do that, the mathematics shows that the only object that would have sufficiently powerful gravitational pull would be a black hole, an enormous black hole, millions of times the mass of the sun. So the case began to be made that these objects are actually real, however much Einstein thought they would not be. But the clincher for the case for black holes actually happens in our era, right? And I'll give you the two vital pieces of discovery that have happened in fairly recent times, and they actually come from Einstein's work himself. So in 1916 and in 1918, Einstein writes two papers. They weren't on black holes per se. They were on the possibility of gravitational waves, right? The basic idea that's being expressed in these mathematical equations is that if space is like a rubber sheet, right? Before I put a bowling ball on it, but now let me leave the sheet nice and flat here. Instead, imagine I go up to the sheet and I start tapping its surface. You all know what will happen. I'll send out a sequence of ripples on the surface, waves, if you will, on the surface of the rubber sheet. Now, Einstein's mathematics basically said, look, if we think about space and time as a dynamical entity, then as objects move through the environment, they should, in essence, tap the rubber sheet, send out ripples in the fabric of space, send out gravitational waves. Now, Einstein himself had a fairly curious relationship with this insight, because over the years, he became quite uncertain of whether these ripples in the fabric of space could be detectable, but even more deeply, whether they were actually real. Because the mathematics of Einstein's theory is so subtle that sometimes even Einstein couldn't quite figure it all out. That's sort of a weird thought, right? You know, Einstein, the equations in the general theory of relativity, they are called the Einstein field equations. And yet, in analyzing those equations, there were issues that Einstein himself had trouble fully coming to terms with. And it wasn't really until the 1960s when the next generation of thinkers took Einstein's ideas and pushed them further that systematic mathematical methods were developed to fully understand what qualities of the equations were mathematical artifacts and what qualities of the mathematical equation should describe something actually out there in the world. And by that point, by the 1960s, it became perfectly clear that if you did have, for instance, two neutron stars or even black holes that were orbiting each other in space, they would disturb the fabric of space and send out these ripples. Now, how would you detect that? Well, the mathematics made it quite clear, too. If you're downstream from these ripples, say if you're on planet Earth far away, then as the waves go by, they will stretch and compress planet Earth. Now, I should emphasize that this video is not to scale. And when you do the calculation, you find that for a typical astrophysical event, the amount by which Earth would be stretched and compressed would be less than an atomic diameter. So now you see the other part of Einstein's discomfort with the notion of gravitational waves. It would seem that they are just undetectable. I mean, how could you ever possibly detect the stretching or compressing of the Earth or an object on the Earth if the amount by which its length changes is a fraction of an atomic diameter? And again, the beauty of the progression of scientific ideas is that, sure, you can be deeply skeptical that you'd ever be able to measure anything like that, but the next generation comes along and says, well, maybe we can. And that's what happened here. So in the 1950s, 1960s, ideas were developed for trying to actually measure these ripples if they're out there. And two machines were built in the United States, one in Washington State, one in Louisiana. And as you can see here, each of these machines involves two arms, basically two tunnels at right angles to each other. So if I match the orientation on the screen, something like this. And the idea is that light beams are sent down these two tunnels, they bounce off of mirrors, and they come back. And when the light recombines, the pattern that arises when the light crosses itself is highly sensitive to the exact distance that the light has traveled. So just to sort of see a picture of what that would be like, if we dive in to one of these tunnels, they're 4-kilometer-long tunnels, you then send a laser beam that goes down the tunnel, races along, hits a mirror at the far end, and comes back. And this is happening in both of those tunnels simultaneously. And the way the light comes back and crosses itself at the center is highly sensitive to the lengths of the two arms, the two tunnels. And that means that if a gravitational wave were to roll by and affect the lengths of these two tunnels, even by a tiny amount, at least according to the calculations, it should affect the way the light crosses itself, the way the light, as we say, interferes with itself as the two wave trains along the two tunnels cross. So this idea was put forward in the 1960s as a means of possibly detecting these ripples in the fabric of space. And thankfully, the National Science Foundation decided to fund the actual building of the devices that I showed you there. And at first, for many decades, nothing turned up. And I should tell you that the general feeling in the community of physicists was that the people working on gravitational wave detection were off the wall. They were doing something that was just impossible, right? And yet they stayed at it. And amazingly, on September 14th of 2015, just 2 days after an upgrade to these machines was put into place, this is what happened. The two detectors twitched for about 200 milliseconds, and they twitched in exactly the same way at two distant locations across the United States. And that coincidence allowed scientists to argue that they had detected the first gravitational wave. Now, I should say, this signal, September of 15, the announcement of a discovery was in February of 16, because during those months, these researchers were desperately trying to prove that this wasn't a real signal, right? They were desperately trying to prove that maybe this was an artifact, or maybe two trees happened to collapse in exactly the same time in Louisiana or Washington State, or the more likely possibility was the team of researchers had put in place a mechanism by which test signals were put into the device to see if everybody was awake and would capture the signal if it was actually there. You know, you put in a test signal and you come in the next day, you say to the graduate student, so, anything interesting happened last night? No, nothing at all. And that's the graduate student that, you know, you send to work on another project in another group, right? So, you know, the researchers, they turn, you know, to the first person who was charged with randomly putting in these test signals and say, did you do it? Wasn't me. You go to the second one, did you do it? No, and they go down the line, and everybody says, I didn't do it. Start to think maybe it's real. And they beat on it, and they beat on it, and they eliminate all other potential explanations and come to the conclusion that it is real. And in fact, they don't just come to the conclusion that the signal is real, they can reverse engineer it. Based on the precise way in which the two devices shook for a fraction of a second, they can figure out what astrophysical event must have happened to give rise to a ripple in the fabric of space that would look just like that by the time it washes by our shores. And the explanation for that signal ultimately is this, and this is where it ties into our theme here. The explanation is that 1.3 billion years ago, two black holes were orbiting each other 1.3 billion light years away. Now, this is a time when there are, you know, single-celled organisms floating around a primordial Earth, right? These two black holes are orbiting each other near the speed of light, and ultimately they smash into each other. And in that collision, they generate a tidal wave in the fabric of space whose energy output is 50 times the energy output of every single star in every single galaxy in the observable universe. You put all that together and it doesn't even match the power of that tidal wave in the fabric of space. Now, that tidal wave in the fabric of space is very far away. It starts to spread out in all directions at the speed of light. So part of it is racing toward planet Earth. Again, nothing happening on planet Earth. But there's a long journey that wave has to travel. And as it travels, it spreads out. And as it spreads, it dilutes. When that wave is about 100,000 light years from us, it goes through the dark matter halo of the Milky Way galaxy, and it continues to race onward, right? And as that wave approaches planet Earth, when it is 100 light years away, about 100 years ago, an individual named Albert Einstein starts to think about the possibility there might be these ripples in the fabric of space, completely unaware that a big one is already racing toward planet Earth, and does these calculations that I've described. Nobody really thinks that you can detect them, but some very prescient researchers, when that wave is about 50 light years away, begin to build the first detector in hopes that it might actually detect one of these ripples in the fabric of space. And when that wave is 2 light days away, they turn on the newly revamped version of that experiment, and 2 days later, that wave washes by planet Earth and gives rise to that signal. Now, if that progression doesn't fill you with awe and reverence for what the human brain is capable of doing, if that doesn't sort of get the heart pounding a little bit, check your pulse. And that's the kind of progression that fills us with utter astonishment. You start with an idea that's crazy mathematics. Some guy in a trench in World War I is fiddling with the equations and gives rise ultimately to a confirmation that 2 black holes collided with each other some time ago. But it's still not the most direct evidence. Even more direct evidence would come from taking a snapshot of a black hole. And that's what another team set out to do, the Event Horizon Telescope, a consortium of radio telescopes around the globe that, by combining the data that they receive, aim to in essence, take a radio photograph of a black hole. And I think as many of you saw, this image was released some months ago, last spring. The first direct image of a black hole. Now, a lot of media interest focused on this photograph, rightfully so. I have to say, though, some folks who, they said it kind of confidentially, they sort of said to me, friends of mine, you know, it's not that great a photo of a black. It's very hard to please, you know, some people. You know, it's only 8 radio telescopes, so it's in some sense, you know, limited in its pixels. You know, people will do better. But the amazing thing to me is, literally 1 week after this photograph was released, a far sharper image of a black hole was, in fact, released. And that, of course, is, as you all know, page 30 of the redacted Mueller report. So, did somebody groan out there? So, this is the culmination of a long journey, but again, it's not the end of a journey. We now know that these things are real, but now we need to deeply understand them. And so what I'll do in the remaining 3 hours is, don't worry, I'll be gentle or reach in the end. In the remaining time, I'm just going to describe some of the theoretical puzzles that we're still grappling with when it comes to black holes. And some of the places we'll get, one place in particular, seems as crazy today as the possibility of black holes must have seemed 100 years ago. That doesn't mean that what I'm about to tell you is true, of course, but it does suggest that it's worthy of detailed scrutiny because the sequence of ideas that we have been following has yielded, ultimately, evidence and data confirming ideas that many of the smartest people on the planet didn't think was actually correct. All right, so the puzzle in particular that I have in mind has to do with what happens to an object when it falls over the edge of a black hole, right? So imagine that there's a black hole out there in space, and I take out my wallet, and I throw my wallet into the black hole. It reaches the edge, the event horizon, as we call it, and it goes over. Now, according to Einstein's equations, when an object falls over the edge of a black hole, it is gone, right? Nothing can get out of a black hole. The gravity is too strong, and therefore, once it goes over the edge, it's finished. Now, that sets up a great deal of tension with our understanding of the universe given to us by quantum mechanics. And I don't have time to go into quantum mechanics in any detail, but I'll just give you the qualitative feel for why this is deeply puzzling. Any object carries information, right? My wallet in particular, it's got obvious information, credit card numbers, photographs, things of that sort, but there's also information in how the molecules and atoms of my wallet are arranged to create that physical structure. And if an object falls over the edge of a black hole and is permanently gone, that means the information content it has is also permanently gone. And if you lose information, if there are sinks of information, then quantum mechanics loses what it requires to make predictions of how the world will unfold. So if information can actually truly be destroyed, then our understanding of how the world progresses will radically change. Now, Stephen Hawking believed for a very long time that information would be lost, just as Mulvaney said, get over it, right? That was the approach that Stephen Hawking took. Many other physicists did not believe that that was a right way of looking at things. And in particular, a resolution to the puzzle was put forward, again theoretically, based on ideas that come from string theory, which goes like this. Imagine you throw your wallet in, and instead of all of the information going into the black hole solely, Imagine that a copy of the information gets smeared out on the edge of the black hole. That can be sort of stored as bits, zeros and ones, schematically drawn here. So much so, the idea would go, that if you recover that information, because it's on the outside of the black hole after all, you could use it to reconstruct any object that went inside. Now, it's not that the wallet didn't fall into the black hole. It did. But the idea is that there's information on the edge, the event horizon, the surface of the black hole, that is able to capture every quality of the object that fell in the wallet, so much so that you could actually rebuild the object if you wanted to. Now, that notion that you can have a three-dimensional object within an environment that's fully described by data on a thin two-dimensional surface that surrounds it should ring a bell. And that bell is holograms, right? So what is a hologram? A hologram is a thin piece of plastic which, when you illuminate it correctly, yields a realistic three-dimensional image. So the idea here is that you can have a three-dimensional object inside of a black hole fully articulated by data on this thin two-dimensional surface that surrounds us. So this gives rise to what's known as the holographic principle. The idea that there's a dual description of the world. You've got the ordinary description that we're familiar with, three-dimensional solid objects, but there's an alternative description using data on a two-dimensional surface that surrounds those objects. Now, this particular case made use, if you will, of black holes in a detailed way, but then people said, look, space inside a black hole where the wallet is, and space outside a black hole, they're basically the same thing. Space is space. So if the wallet inside the black hole can be described by data on a surface that surrounds it, maybe that's true absolutely everywhere. Maybe every three-dimensional object, regardless of where it is, has a dual, alternative description as a hologram, data stored on a two-dimensional surface that surrounds it. So an image that you might have would be this. I don't know if you can see it. Hopefully you can back there. I can't see it up here. But say this is planet Earth. Can you see the holographic surface that surrounds it, which holds information that describes the comings and goings of everything that happens in that real three-dimensional world, but stored on a two-dimensional surface? So this notion that emerges from these ideas suggests that you and I and everything else, we are just the holographic projection of data that lives on a distant, thin, two-dimensional surface, perhaps at the boundary of the observable universe, not illuminated by a laser with a real hologram, but rather illuminated by the laws of physics. You and I are just holograms. Now, it's right to chuckle at that idea. It's a strange idea, but nevertheless, it's where this sequence of ideas has taken us. Now, whether it's right or wrong will have to be ultimately determined by future experiments, future observations. But to me, it's utterly remarkable how simply by sort of following the dots, starting with Einstein and the development of his equations, we come to a picture of the world that does sound absurd. And yet, that absurd picture may actually be right. Now, I could stop here, but there was one other thing I was going to tell you about, but you'll have to tell me if you've got patience for one other crazy idea. You all right? All right, so I'll go through it relatively quickly as time is short. And the ideas are a little bit tricky, so to fully explain them would take a long time. So I'm now going to cater a little bit more to those who have some familiarity with some of these concepts. But the final thing I'll tell you about is this. We're now approaching the 85th anniversary of two other papers of Albert Einstein. On May 15th of 1935, Einstein wrote a paper with two colleagues, Podolsky and Rosen, on something called quantum entanglement. How many people are familiar with that idea? A lot of you. So that's the idea that you can have two distant objects that somehow behave as though they're connected by invisible quantum threads. A very strange idea, again, one that Einstein resisted. His paper was basically trying to say, look how crazy it is that quantum mechanics is suggesting this possibility, but yet we now believe that it's not just crazy, it's right. Second paper that Einstein wrote in 1935 was in June of 1935, a paper, again with Nathan Rosen. Podolsky was not part of this paper. And the second paper was on the idea of wormholes, right? Everybody's encountered that idea. If you watch Deep Space Nine or any number of science fiction films, have the notion of wormholes, which are tunnels that connect two distant regions of space. Einstein did not think that these two papers had anything to do with each other, completely different ideas. And yet, in the last few years, we've come to think that those two 1935 papers may be deeply connected, and the connection may actually explain how the fabric of space itself is actually threaded. And that's what I'm going to spend my last 6 minutes quickly describing to you. So, the first idea, this idea of wormholes, just to give you a picture to have in mind, imagine you've got two distant regions that create a kind of tunnel between them, a kind of shortcut between one region of space and another. So that's the paper, I think I said June, actually I think it's July of 1935, that Einstein comes up with this idea, solves the equations of general relativity, and shows that you could, in principle, have structures like this. And here's the other idea, quantum entanglement, the May paper, in which you can have two distant particles that are somehow connected by these invisible quantum threads. And for me to describe what I want to tell you about, I've got to be a little bit more precise, certainly on the entanglement and idea. And to do that, I'm going to use the canonical example that everybody talks about with entanglement, which has to do with spin. Particles in the world, elementary particles, all spin around like little tops. Amazingly, they can only spin in one of two directions, clockwise or counterclockwise. And if it's counterclockwise, we call it spin up. If it's clockwise, we call it spin down. Now, the weird thing of quantum mechanics is it describes the world in probabilistic terms. So you can have a particle that's 50% spinning up and 50% chance of spinning down, actually hovering in a mixture of two of those possibilities simultaneously. And only when you measure the particle does it kind of snap out of the haze and spin up, or snap out of the haze and spin down. That's the weirdness of quantum physics. Now, I want you to take this idea with me one step further, because what Einstein was imagining is two particles, each of which is spinning up and down simultaneously. You separate them very far apart, and according to his calculations, if you measure one particle and it snaps out of the haze, the distant particle also must snap out of the haze, even though you didn't do anything to it. That, Einstein said, is spooky. Do something here, affecting something over there. And that was his argument. The world can't be spooky, and therefore quantum mechanics cannot be a full theory of the world. But the reality of it is, this kind of effect is now observed all the time. So you have two distant particles, say one in Las Vegas, the other in New York. I go over to the one in Las Vegas, I measure it, and the one in New York is forced out of the quantum haze at the same moment. A very, very strange idea. But this quantum entanglement, we think, together with Einstein's idea of wormholes, may actually give us our deepest understanding of the fabric of space, and it goes like this. So imagine I focus in on a black hole. And that black hole, say, could be floating in space. And as I mentioned before, this holographic idea tells us that this black hole has an alternative description in terms of a thin sphere that surrounds it, basically at the event horizon. So in order to show that, I'm going to go down to sort of a two-dimensional version that's easier for us to see. And that red surface there is the holographic surface surrounding the black hole, again, one dimension lower, just for visualization purposes. The new idea is this. Imagine we have two copies, that is, two black holes. Each is described in this holographic language as a surface that surrounds it. And imagine further that we take Einstein's idea of quantum entanglement and we entangle those two outer surfaces. What would that entail for the geometry of the interior region? And here is the beautiful insight. Calculations reveal that entangling the stuff on the outside is tantamount to connecting the inner stuff with a wormhole. So here are two of Einstein's ideas from 1935, entanglement on the outside and wormholes on the inside, and we recognize that they are the same thing, just described in two different languages. Einstein, I think, would be shocked in many ways by the picture I'm showing you right here, but it's a picture that comes right out of our analysis with string theory. And in fact, some researchers have taken this picture and pushed it even a little further, because they have realized that that entanglement that I'm showing you connecting these two copies of a black hole, two black holes if you will, you can actually apply this entanglement to one copy. You can entangle that outer surface with itself. And when you do that, there's something amazing that pops out of the equations. If you start to cut the lines of entanglement, look at the entanglement line, the yellow line at the top. I'm about to cut it right now. So there it goes. I'm going to cut that guy away. What does that imply for the geometry in the inner description? It entails that the geometry gets cut in half. The actual space itself gets cut in half if you sever some of the lines of quantum entanglement. And now I'm going to keep on doing that. I'm going to cut more and more lines. I'm going to cut some on the left. What does that correspond to? It corresponds to also cutting the space further in half in another way. And now I'm just going to sort of let this go. Cut lines of entanglement, see what it does to the geometry. And the geometry basically pixelates. It falls apart. Which means if I turn this story around backwards, in order to have a fabric of space, you have to stitch together the individual plaquettes, the individual pixels. How do you stitch them together? You stitch it together with the threads of quantum entanglement. So the fabric of space itself may emerge from an idea that Einstein didn't like, but yet introduced with his paper on entanglement. The fabric of space may be stitched with the threads of quantum entanglement. Again, a wild, strange, crazy-sounding idea, but naturally comes out of the mathematics, and we have sort of grown to have a degree of confidence. Not necessarily that all math tells us the true workings of the world, but certainly is worth our focus to try to determine whether these ideas are right or wrong, because the payoff and the depth of understanding would be utterly astounding. So I will conclude here. Thank you very much.